Thanks for the
Merci.
sympathy.
Merci, Jean-Eric.
Thanks.
It's a real pleasure for me to introduce Daniel Lincot. He has worked in photovoltaics for over 40 years, and he served as the director of l'Institut Photovoltaic de France for several years, fairly recently. And it's always been a pleasure for us from abroad to visit with Daniel, both in his laboratory and to participate in meetings and workshops that he has organized. He's consistently treated us to both his science and also to sample the French cuisine and wine while we were in Paris. Daniel has always had a passion for photoelectric chemistry, and that gives him a direct link to the original discovery of Edmond Becquerel. Today, his presentation is entitled A Modern Interpretation of a Photovoltaic Effect Discovery. Daniel, s'il vous plaît.
Thank you very much, Jim. It's a pleasure to have you as a chairman. We also know each other from very, very long time, and it's great to also, thanks to the online symposium, it's great to be able to have you on the floor also. So, hello everybody. So, je vais parler en français.
I'm going to switch to French and to talk about the modern interpretation of the photovoltaic effect. My presentation now.
As indicated, I'm working at the IPVF, the Photovoltaic Institute for the Greater Paris area. Can you help me, please? How do I get rid of this? I just want to see my slides. Wonderful, thank you so much. Let's discuss first the historic recognition of the discovery by Edmond Becquerel of the photovoltaic impact or effect. I think it's important to understand exactly when this happened, how it happened, where it happened. I'm referring to recognition of this photovoltaic impact. So as a guiding theme, because I decided to do things properly, right? So how does photovoltaics work? And I have a guiding theme for all of the participants, or rather I have a question for you. What is the relationship between all three objects? On the left-hand side is one of those tricks you find in carnival fairs, and you use this hammer to punch and measure your own strength. And the stronger you use the hammer, the higher you will reach. And the goal is to reach the clown's head. And the second object in the middle that I'm going to ask you to think about is what we call a Fluence Ball. And my generation loved Fluence Ball. And this is an interesting one because it's called Voltaire. And the third aspect is on the right-hand side, and this is what we're here today to discuss. It is a photovoltaic module. Okay, let me start this presentation by discussing recognition of Edmond Becquerel's contribution. Let's go back to 1931. These are the first references to photovoltaics. It took about a century, isn't it? So La Nature is the ancestor of a publication now called La Recherche. It is a high-level scientific dissemination publication. And there's a whole article on the very first photovoltaic cells. So the very first photovoltaic and photoelectric cells. This is a very interesting article because it takes stock of the state of the art at the time. And there's one paragraph in this article that attracted my attention, and it will resonate with Ms. Blondet's presentation. the general public all too often believes that the very first electric effects of light were discovered in 1873 when British engineer May, assistant to Willoughby Smith, discovered fortuitously the photoresistant properties of selenium at the Valencia telegraph station, but that is not the case at all. And one must recognize when it comes to the observation of the very first photoelectric phenomena that French scientist Edmond Becquerel has priority. So, for nearly a century, Edmond Becquerel's contribution was forgotten, and then the world of physics rediscovered the photoelectric effect, and they forgot about Becquerel, and they preferred solid state systems because Becquerel systems were a little complicated. They were electrochemical in nature. So, from a scientific point of view, I continue to quote, they have the remarkable property of directly transforming light energy into electric energy. And this is where things get interesting and may someday be used as current generators. Now, he means power, not current, but we understand his meaning. Now, what's really interesting is that the French are all hands on deck to try to ensure recognition for Becquerel. But on the other side of the Atlantic Ocean, Physical Review, which is a famous publication, well, in 1932, they don't hesitate. They don't mince words. They call it the Becquerel effect as a special case of the barrier layer photoelectric cell. So this photoelectric effect was discovered and turned into an equation by Walter Schottky in 1930. So all of a sudden, Becquerel is back in the limelight, and he is referred to as the discoverer of this effect. And all of a sudden, it is suggested that there is an essential identity. In other words, we're talking about the same thing. And it's important that this is happening as early as 1932. Now, 1959, silicon, the photovoltaic effect and its utilization by Paul Rappaport. If I remember correctly, that was the first recipient of the William Cherry Award in the US. So it is 100 years ago that Becquerel discovered the photovoltaic effect. So Adams and Day were the first to observe this in a selenium-based solid cell nearly 40 years later. So this was the very beginning of the article. This is what the article says in its introduction. So what's really interesting is that throughout the period, people were well aware of the photovoltaic effects associated with Becquerel. What's interesting is that people such as Ratton and Gary used Edmond Becquerel's method to characterize new semiconductors such as germanium, silicon, and this entire theory was based on water diodes. And here again, they recognize Becquerel's contribution to discovering the first photovoltaic effect, and they describe it. And what they show is really interesting. What you see at the bottom is what you find in every single class book in reference to these Schottky or barrier-based diodes. Sorry for this walk down memory lane. I'll be quick, I promise. Martin Worth in 1972 has zero doubt. And he goes over the entire history, the historical development of solar cells. See the discovery of a silicon by Berzelius, and then the photovoltaic effect discovered by Becquerel, and then you move on to photoconductive effects, and then Becquerel is back in 1918. Goldman and Brodsky refer to Becquerel. As you can see, Becquerel is referred to twice in the history of photovoltaics. Now, how do we tie in with the future? This is a very important article published in 1972 in Nature. Well, it's a different Nature than our Nature. It's a different publication. But this is a seminal article published in 1972 by Fujishima and Honda. And these two authors discovered that using photoelectrodes, one could dissociate water. In other words, this is a Becquerel cell, which photodissociates water. And this is a highly topical issue. So using light to dissociate water. See, this looks very much like a Becquerel cell. The Becquerel cell that Jérôme Fatté showed us a minute ago. And then 4 years later, in 1976, again, the Becquerel effect solar cell. And in the conclusion, you see, I quote, it appears that a Becquerel effect solar cell is capable of conversion efficiencies of technological significance, end of quote. And this is really interesting. In other words, this is the prospect that the Becquerel cell can be used for technology, for producing electrical current, power, using electrochemistry. So let's take a closer look at Edmond Becquerel's original article in 1839. This was published in the Compte Rendu de l'Académie des Sciences, basically the French Academy of Science proceedings. And this is a memorandum on the electrical effects produced under the influence of sun rays, written by Mr. Edmond Becquerel. There's no ambiguity here. There's no other person signing this memorandum. He signed it in his own name. So as shown by Jérôme Fatté earlier, these are the types of cells that he used back in the day. Now, in paragraph 2, and this is important, you find electrical currents developed by the breakdown of chloride, bromide, silver chloride, bromide, and iodide under the influence of solar light. He explained it, and he was a really good chemist, a very good electrochemist, and a very good assistant. He made silver chloride, and it applied silver chloride layers on platinum plates. Now, the Becquerel discovery, when it works with orange or red lights, there's no current, but when it goes up to the UV region, the current goes up all the way to 3 degrees, and things become stabilized when you get into the blue region. And this is a seminal discovery. So this is what he concludes, and it's pretty surprising. And this ties in with what Jérôme Fatté said before. He truly and strongly distinguishes the electrical impact. He says this has nothing to do with heat. There's no thermal source. And here again, he's trying to measure what's happening. The breakdown of silver chloride, bromide, and iodine under the influence of light produces electrical effects that can be used to determine the number of active chemical rays. So obviously, at the time, he didn't talk about power generation. But what's important is the absorption of light in silver chloride produces an electric current for the first time. And I believe this is the very first discovery Edmond Becquerel made. Now, this is a diagram of the actinometer. Jérôme Fatté discussed this at great length. So let's get back to the interpretation of things and his results. Now, he was an experimenter, and you see this on the left-hand side. And on the right-hand side, this is our modern interpretation. Let's start at the beginning. What do all these colors mean? Red, green, etc. We know that there are different light waves. So 400 nanometers for the visible all the way to the infrared, etc. So there's a whole spectrum where we're able to reposition Edmond's colors quantitatively on the basis of wavelengths. And what we find is that there is no current intensity until you get to the UV region, and then you clearly see there's a threshold effect. So what about this threshold effect? It is important. This is exactly the type of threshold effect we observed years later. Hertz and Lena discovered the photoelectric effect. So it is the exact same threshold effect. So let's go one step further. At the end of the day, we have the photon concept, and what Einstein showed is that photons are reversely correlated with the wavelength. So the threshold of 450 or 500 nanometers means about 2.7 electron volts, and this is what we call the threshold effect. This is what we call the gap band. So Edmond Becquerel showed Pretty much the same thing, obviously. We're stuck between two different levels here. This is the equivalent of the photoelectric effect that Becquerel showed. Now, getting back to our trick question, let's try to connect that trick question with what happens in actual fact. Now, this strong man, what does he do? He has his hammer and he bangs real hard. And it does pretty much the same thing as a photon entering a material. The photon will hit the matter. And the stronger you are, the more likely you are to reach all the way to the clown's head. The only difference is that that pellet is replaced by an electron. And the electron was very happy in its hole. And because the photon excites it, the electron gathers the photon's energy, and this is transformed into electrical energy. So the electron is excited into a higher level of energy. It goes up to 2.3, 2.4, 2.5 electron volts. Basically the electron steals the photon's energy, and this is in the form of electricity. E equals minus QV. This means we change the potential of the electron, and what we find is something really interesting. The first action of light on a material is basically an energy, a magnetic energy to electric energy conversion. This is a great analogy. So what does the electron do? Well, it ends up going back to its initial state and recombines with this hole. This is what happens. So you've excited it into a higher level of energy, and eventually the electron goes back to where it was meant to be by releasing energy or light or heat. So we're moving into the ins and outs of the photovoltaic effects. So what about the Fluence Ball? What are we doing here? We're no longer dealing with a strong man wielding a hammer, but we have a spin. We have a coil, and the coil will bump against the steel ball. The steel ball will go up. And what's interesting is that if you don't hit hard enough, the ball will fall back down. And sometimes you get the exact right energy level. And there's a slight slope here. And so the ball gets out and gets to work. The ball is not going to lose energy in the form of heat. No, it's going to transform this potential energy into a mechanical energy. And the ball in the Fluence Ball will do whatever it wants and eventually get back to its beginning. So the photon is symbolized here by the coil, which punches up the steel ball. And we see the metaphor. And we've been able to transform the potential energy into mechanical energy. In other words, we've transformed it into work. So what happened here? What do we see? When we light up, when we expose to light the silver chloride, we have two different levels of energy, the low level and the high level, which match the two times in the Fluence Ball when the electron goes up and then comes back down. Now, this is the equivalent of photography. What do we mean by that? These electrons and these holes, instead of the ball going back down into the Fluence Ball, there's going to be an electrical chemical reaction in the electrolytes. What the electron wants is simple. It wants to reduce it wants to achieve a reduction reaction. And so you have highly oxidizing species here with the very positive potential. And so it is possible to oxidize the chloride into chlorine and even oxidize water to turn that into oxygen. So at the end of the day, you have AgCl plus Hv, that's the proton, gives Ag plus 1/2 of Cl2. What you do is create silver. And we have formed silver clusters in the band gap. So that's all well and good. But what you're telling us, you may retort, what you're telling us about photography, but what is the connection between photography and Becquerel? Well, Becquerel apply that layer to a platinum plate. And there's an anode and a cathode. And what happens here? There's a barrier that is formed. And as a result, the two plates, the two exit plates are tilted. Remember, the electron has a negative charge. So what happens is there's an electrical field at the interface, and the electrons are going to go in the opposite direction. So they go into the selection and they will oxidize the holes. And we end up with a real solar cells. And the electrical current can get out. This is case number 1. Let's call it the type 1 photovoltaic cell. Now type 2, this is a different case scenario. What's interesting here is that when you change the metal, when you use platinum or silver, you end up with the type 2 or the type 1 photovoltaic cell. And here, the two plates are oriented the other way. So the electrical field, instead of bringing the electrons to the solution, it brings them back to the other direction. We have switched directions. So a different type of solar cell, but it's still a photovoltaic cell. And you can measure the electrical current and you can measure its efficiency. This is the equivalent of an all-solid Schottky solar cell. Now, you can find online Dick Swanson's video testimonial. He used copper oxide and he showed, see, there's a current that is being created and the efficiency is 0.0024. So we can do 10,000 times better using silicone cells now. That's the situation. And what's interesting is that all of this work is found in the most advanced publications. This is a publication by Martin Lenz, David Church, and Jayan Calzaferi. I knew them back. I bumped into these names back in the days when I used to read a lot about electrochemistry. And as you can see, it is possible to photooxidize water using AgCl electrodes and also tin oxide. So these are very, very weak currents, microamps. What's interesting is that when you light up the light, the current goes up. When you turn off the light, the current goes down. And this matches the production of oxygen. And on the right-hand side, you have an energetic diagram. And as you can see, you are well positioned, a bit like the Fluence Ball. The electrons are able to reduce the protons, and the silver and the holes are able to oxidize the water. So this is really interesting work. Here's the situation. We now understand the whole carnival metaphor. You turn the hammer into a photon. In other words, the hammer is the photon. That strong man there is the sun, wielding the hammer that is sending the photon, and the material is, well, the whole clown tower. And Edmond Becquerel did the same thing with electricity and photons, and then you have silicon solar cells, which emerged in 1954. And now we have other types of cells, dye cells. Michael Kretzel does a wonderful presentation on that in the video testimonials, and then perovskite solar cells, which is a tremendous scientific advance. Now we're talking chlorides and bromides and iodides, so we're back to Becquerel's work. To some extent, Becquerel made huge contribution to photovoltaics, light, electricity, something that's analogous to the photoelectric effect. Obviously, I'm referring to the discovery of the photoelectric effect, but also electrochemical cells, semiconductors. Thank you very much for your attention. And of course, I'm looking forward to going back to my Fluence Ball. Thank you very much.
And thank you very much, Danielle. I don't think we have a specific question from the audience, but several people expressed their appreciation for your analogies with the strong man of a carnival and with the flippers of a pinball machine. So I think that you've enlightened us as to maybe a slightly different way to view the photovoltaic effect. So thank you. And we will now move on, I think, to the next session.